Hello everyone, welcome to another video on statistics. I am still busy with Statistical Inference 1, STA 1502, and I'm still busy with assignments from the 2023 academic year, and we're still working on assignment 1, and today I'm starting on question number 3. Now questions 3 and 4 involve what we call matched pairs experiment. So I want to give a brief explanation of the concept matched pairs experiment. So we have matched pairs experiment, questions 3 and 4, like I said. It involves two normally distributed populations that are dependent. The parameter of interest is the mean of differences of pairs, and that's X bar D, capital D there. Let's look at two examples just to add more substance to the introduction there. Example 1, the effect of the teacher's dress code on learner performance. So we have kind of an experiment here. So item number 1 says, in term 1, let a teacher dress casually and administer 5 tests. In term 2, let the same teacher dress officially and administer 5 tests to the same learners. After that, take scores of 10 learners from this teacher's class and determine their averages for each term. Then compare term 1 results with term 2 results. This would help us determine whether the teacher's dress code has an effect on the learner performance or not. All right, let's move on to example number 2 that I would like to talk about. So example number 2 involves comparing German-made cars and American-made cars in terms of comfortability using the ratings from 1 very uncomfortable to 8 very comfortable. Like we said in example number 1, this is an experiment. Remember, matched pairs experiment. So we say take 10 people, let 10 people ride a German-made car from city A to city B, a distance of 8 kilometers, and back to city A. Let the same 10 people ride an American-made car from city A to city B and back to city A. Let the 10 people individually rate the car's comfortability levels for each ride. And then you have to compare the ratings of the two cars. This would help us determine which car model is more comfortable. So these are the two examples that I put up just to give more clarity on the concept of matched pairs experiment. Now let's look at question number 3. Question number 3, here it is. It says 9 experts from a company have rated 2 brands of coffee in a testing experiment. The following rating choices were given to the experts: 1 being extremely unpleasing, all the way to 7 being extremely pleasing, for each of the 4 characteristics, that's taste, aroma, richness, and acidity. The data for the summated ratings accumulated over all 4 characteristics are shown below. So we have brand A and brand B, and these are the data for brand A and brand B. Now the question continues. A statistician wants to determine whether the 2 population means differ at 10% level of significance. The 2 samples are assumed to be dependent. You see, there it is now, matched pairs experiment. I told you it involves dependent populations. So here it says the 2 samples are assumed to be dependent and normally distributed. For testing, the null hypothesis H naught, that's mu D is equal to 0, against the alternative hypothesis mu, that's H1 mu D, being not equal to 0. Which of the following statements is incorrect? Now this is hypothesis testing, but the concept is matched pairs experiment. So I want us to go through this from the hypothesis testing perspective. And you would recall that we have 6 steps to execute. So let's look at step number 1. So this is page 3, and we're looking at question number 3. Step 1, what do we do? In step 1, we state the null hypothesis. They have already given us that, which is mu D is equal to 0. And the alternative hypothesis, mu D is not equal to 0. Now notice when it says not equal to 0, no direction has been given. Again, you have what we call here a two-tailed test. two-tail test. We have a two-tail test there. Right, so step 1 completed. We're moving on to step number 2. If you remember, in step number 2, this is where we state the alpha level, and the question has told us here that we have 10% level of significance. That's alpha. So alpha equals 10%, and we know that 10% is 0.1. But remember, when you have a two-tail test, alpha has to be divided by 2. So therefore, alpha over 2 will be equal to 0.10 all over 2. And what does the calculator say? The calculator says 0.1 divided by 2, and the answer is 0.05. So 0.05. This is the value of alpha over 2. And remember, matched pairs experiment involves what we call the student t distribution, and therefore we have to work out what we call the number of degrees of freedom. So degrees of freedom, df, is equal to number of differences minus 1. And this is gonna, in this case, if I take you back to the table here, number of differences, we will have to rewrite these numbers in a vertical format where we actually work out differences between the two. So number of differences will be equal to number of pairs. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 differences, or 9 pairs. So our n is 9. So we're going to say 9 minus 1, and the answer is 8. So we have 8 degrees of freedom. Right. Step number 2 completed. We now must move to step number 3. And in step number 3, if you would recall, this is where we calculate what we call the critical value. And what is the critical value? Just to remind you, it's a value that separates the rejection region from the failed to reject region. So step number 3. So in step number 3, we work out T critical. So T crit, remember we're using the student T distribution here now. T crit will be equal to T. We state the alpha over 2 value, 0.5, and then we indicate the degrees of freedom, 8 degrees of freedom. And then we go to the student T distribution and pick out the critical value from there. So here is the student T distribution. And remember, the value we have for 1 tail is what we are working out here by dividing by 2. This is for 1 tail. For 2 tail is for two tails, this is the value 0.10. For 1 tail, 0.05. So remember that for 1 tail, so we're looking at 1 tail. There it is, 1 tail, 0.05. 2 tails, it must be 0.1. So here it is, 0.05 for 1 tail and 0.1 for 2 tails. And we have 8 degrees of freedom, so we must move from left, like I've explained in the previous videos. I want to demonstrate that again. So 8 degrees of freedom from left, here we go. So 8 degrees of freedom, and we're stopping at 0.1 or 0.05 for a single tail. So there you go. So 8 degrees of freedom, our answer is 1.860. That's our critical value, 1.860. So T critical is 1. Remember now, it's a two-tail test, so it has to be plus or minus by symmetry. So 1.860, if I remember correctly, 1.860. Yes, 860. That's correct. 1.860. That's the critical value right there. Right. Step number 3. This is all we do in step number 3. Now in step number 4, we have to perform a lot of calculations, because that's where we determine the test statistic. Now looking at the space I have here, this space is not sufficient. So allow me to move to the back. So I'm going to just say step number 4, I need a separate page for that. So here is step 4, and I'm going to go to page 4 here. And step 4. Now in step 4, remember this is where we perform calculation of the test statistic. But what I want to do first is to write down the data for step 4. So let's get our question paper. Then here is our question paper. These are the values. Now I'm going to write these values in a vertical format or vertical order as follows. So I'm going to have brand A, brand B, and then I'm going to work out what we call differences. So I'm going to write here diff, and your differences is what we call XD, right? So we have 9 sets. So let me just use a ruler here, if I may, as quickly as I can. So we are going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 over here, all the way up to there. So I'm gonna have to have this here. Yeah, somewhere like that. From here down here, moving up, and then I also have from here going up, and then we have differences here. Okay, so here we go, differences. All right, now hopefully it doesn't take too much time. There you go. I'm going to take advantage of the margins and the lines in the page to try and avoid redrawing those pages. So here we go. So let's put up the values then. So we have brand A. Remember how we are writing them down? It's 24, 26. So it's 24, 26. And then we have 27, 27. Here it is, 27, 27. The 19, 22, and so on. 19, 22, and then I have 24, 27, 27, and then I have 22, 25, and then I have 26, 27, and then I have 27, 20, 26, 27, 26, yeah, 27, 26, then I have 25, 27, and finally I have 22, 23. Then we work out differences. So exactly how these numbers are, we subtract them. So it will be 24, just showing here minus 26, and the answer is minus 2. So you have minus 2 here, and the next value is going to be 0, obviously. And then here it will be minus 3. You can check that, and this will be minus 3 also, and then minus 3 also, and there it will be minus 1, and there it will be 1, and then here it will be minus 2 and minus 1, right? So what we need to do now is to work out the mean of these values and minimal parameters. So let's look at the first parameter we need to determine. It's going to be our can I write it this side? Yes, I have space there. So we have x bar d. We write down the answer, and then we have, obviously, maybe right at the top there, nd. We already worked out this one. It's 9. You can see here number of differences: 1, 2, 3, 4, 5, 6, 7, 8, 9. And then x bar d, we're gonna work that one out. And then we are talking about the standard deviation of differences. We're gonna write it down. We need those numbers in our determination of many other concepts. All right, so let's enter these values in the calculator. If you remember from the previous video, I'm going to show you again. We're going to say setup or mode button and choose statistics, which is STAT, and then just go to AC button there, and then shift 1 and then 2. You have 2 columns there, the X column, and then you have the frequency column. So frequency column, the calculator does put the values for you there. So you just enter each value one time. So minus 2, press the equal button, and then 0, press the equal button, then minus 3, equal button, minus 3, equal button, minus 3, equal button. Here you have to be extremely careful because all the calculations are actually hinged on your accuracy on the table there. So next is 1, I believe, minus 1, 1, yes, and then minus 2, and then minus 1, right. Let's just check if we've entered all the numbers correctly. I press the AC button and then shift 1 and then choose var, VAR, and then choose small letter n and press the equal button. The answer is 9. Correct. Now we're moving on to X bar D. AC button again, shift 1 4 for var, and then X bar there, number 2 on my calculator here. The answer is -1. So this is -1.555. I'm going to round off this number to 4 decimal places. So that should be 6. So that is my X bar D. Let's look at the standard deviation. But remember, now this is the sample standard deviation. We're going to use SX on the calculator. AC button again, shift 1, and I'm choosing var again. And then we have number 4 there, SX, and not mu X, because mu X is population standard deviation. And here we're dealing with the sample, so it has to be SX. Number 4, my calculator says 1.4240. 1.4240, and that's my standard deviation of differences. All right, now I have to work out the parameters of interest. Number 1, I'm going to work out the test statistic, which of course step number 4 is basically aimed at that. So test statistic, I'm going to say T stat. The formula says X bar, that's your D, minus mu D all over SD divided by square root of ND. Right. Now let's punch in the numbers. I'm gonna have to come this side maybe. Hopefully I can have sufficient space. I do have space. Okay. So this is equal to X bar, that's minus 1.5556 minus, remember mu D is actually 0. Let me just get the page where we wrote the alternative hypothesis. Here we go. Hypothesized population difference, that's mu D 0. That's the number we're using in our calculation of the test statistics. So minus 0 all over the SD is 1.4240, and we're dividing this by square root of 9. Let me put this in brackets like so. As you would recall, I like to punch all that into a calculator one time. It improves the level of accuracy. So I have here, okay, let me go back to computation. That's setup or mode computation. So I'm now talking about minus 1.5556 minus 0, obviously it's the same number, and then all over, let me put a bracket there, and then I have 1.4240, 1.424 or 1.4240. It doesn't really matter. All over square root of 9, which we know is 3. And then let's just close this bracket here. My calculator says minus 3.2772, minus 3.2772 to 4 decimal places. That is my test statistic. One parameter of interest, like I told you, this is the main parameter of interest, but we know that we actually determine other aspects as well. Like the next one, I'm going to call it the standard error, capital S, capital E of the mean of differences is going to be equal to the denominator, which is SD all over square root of ND. This is 1.4240. 1.4240. My hand misbehaved there. Let me just remove this 0 here. 1.4240, and then we're dividing that by I'll come back and fix that. We're dividing that by square root of 9. So this will be all over square root of 9. We know that that's 3. So the answer would be, let's just get the answer down. So we are saying now, so we are saying 1.4240 divided by square root of 9. We know the answer is 3. Our answer is 0.4747 to 4 decimal places. 0.4747 to 4 decimal places. Right. And then here, let's just fix it, this one up. It's 1.4240. 1.4240. Right, like that. Now, next, remember, The next item we need to work out is what we call error bound for the mean of differences, EBM. EBM. Some lecturers don't like to compute that. They like to compute everything together when you're determining the confidence interval. But I like to separate it like this. So EBM is going to be your T alpha over 2 times the standard error of the mean of differences. So alpha over 2, we have that value. It's called the critical value. Here it is, 1.860. Remember, we don't take the minus sign. We just take the positive value. The minus sign, the plus or minus, I told you these signs are given because of the two-tail test and symmetry. Right, but it's 1.860. So here I have 1.860 times this number here is this one we computed here, 0.4747, and my calculator says so it's 1.860, 1.86 times 0.4747. My calculator says 0.8829, 0.8829. This is the error bound for the differences, the mean of differences, EBM. Right, now we need to work out the confidence interval, and then I'm moving on to step number 5, which is the decision rule step. So page 5, confidence interval, which is next. And remember, our alpha level is 10%. The question says 10% level of significance, and therefore level of confidence will be 100 minus 10%. 100% minus 10%, which is 90%. So we're actually constructing a 90% confidence interval here. Right, so here we go. Our next item or next parameter we need to work out is actually not a parameter, an interval. 90% CI, confidence interval, for the population mean of differences will be equal to X bar D plus or minus EBM. So handy. This one, X bar D, if you remember, is minus 1.5556. And then we have plus or minus EBM is 0.8829. Let me just take you back here. The X bar D is minus 1.55, minus 1.5556. And then error bound for the mean of differences, 0.8829. There it is. All right, and that's what I've written down here. So now let's work out the lower class level. LCL is minus 1.5556, and then we're going to say minus 0.8829. The calculator says minus 2.439. I'm going to round off to 3 decimal places just to increase the levels of accuracy. So minus 2.439. And then we are to write down the upper level, lower class level LCL. In some books, they'll call this LCL, lower class level. And then we are going to work out the upper class level by changing that sign to plus, like so. And this is equal to minus 0.673 minus to 3 decimal places, minus 0.673 to 3 decimal places. So this is upper class level. Right, so these are the numbers we got for our 90% confidence interval. What are we saying basically? We are saying that we are 90% sure or confident that the mean of differences is less than this number here, minus 0.673, but is greater than minus 2.439. In other words, it's in that interval. If you are to talk about the real number line, this is how it would look, but we're wasting time. But anyway, let's just explain it. So we're saying on the real number line, this number is smaller than this number. Always the smaller number will be on the left because you're dealing with a real number line. So this is minus 2.439 all the way up to minus 0.673. Let me explain to you that 0 is somewhere this side. That's where 0 is. So we're interested in that one there. That's your confidence interval. We are saying basically that this mu d here is in that interval, and we are 99% and 90% confident that this is where it is. Right. Now I am moving now to step number 5. Step 5, we usually stop at step 5 if the question does not have any specific claim. And in step 5, this is the decision rule step. Decision rule step, if you remember. And what are we saying here? We're saying reject the null hypothesis if, like in this case now, we're saying T critical, T stat actually, is greater than our T critical, which is, I'm going to write the actual value here now, 1.860, or our T stat is less than minus 1.860. Why am I saying this? Because this is a two-tailed test, so we must have plus or minus. There is your plus sign there. That number is positive and that number is negative. Now what does this mean on the distribution curve, the normal distribution curve? Of course we call it the student T distribution, which is basically the normal distribution curve with varying levels of degrees of freedom. So it will look like this. And obviously we know that this is symmetrical about 0, the center there, and we are saying that let's say this is 1.860, and then by symmetry we are talking about somewhere here we're going to have minus 1.860. Here are our two tails, the two-tail test. There's a tail here and there's a tail here. Area under, or the shaded area there, is your alpha over 2, and we say that this is 0.05. Same story this side, area there is alpha over 2, which is 0.05, the shaded area there, right? The center there, the unshaded part, is your 90% confidence interval, or the region, the failed to reject region, rejection region 2, and the failed to reject region there. Now let's compare our test statistic with the two critical values. Where is our test statistic? Here is our test statistic, which is minus 3.2772. So where does it fall, this number? Obviously, you'll agree with me that it falls somewhere this side in the rejection region on the left. So this is where you have minus 3.2772. It falls in the rejection region. So what is our story then? What is our decision? We reject, therefore, we reject HO. And I told you last time that when HO is rejected, it means the hypothesized mean of differences is not in the confidence interval. But let's check. What is our hypothesized mean of differences? Our hypothesized mean of differences is actually 0. There it is. That's our hypothesized mean of differences. Is that number in our confidence interval? You'll agree with me that it's not in there. I told you that 0 is somewhere this side. So the confidence interval and our traditional approach of comparing the critical value and the test statistic and the critical values, these two approaches must say the same thing. If H naught is rejected here, it means the hypothesized mean difference is not in the confidence interval. And it follows that if the mean difference is not there, here, if you approach it from this angle here, you'll see that the test statistic falls in the rejection region. Now the p-value, if H naught is rejected, you would recall that the p-value, if I may just say here, the p-value, if H naught is rejected, the p-value is greater than alpha. Please take note of this. The p-value is greater than alpha, and if you can use Excel, you'll actually confirm that alpha is actually greater than 0.10 in this case, because here we're talking about 10% level of significance. So this is what we have. Use Excel, you'll actually agree with me that the value, sorry, here I'm making a mistake. The p-value is actually greater than 0.1. Let me rewrite this part here. My hand misbehaved there. So I'm saying the p-value is greater than 10%. I must just fix this one up before I conclude this particular video. We will not tackle question 4 in this one, otherwise the time would be too much. I'll have to record another video for question number 4. So p-value here is greater than 10%. So that's basically what we're saying, because alpha is 10% according to this question here. All right, I am trusting that this video has been useful. If you're new to the channel, please support us by subscribing and inviting friends to come and subscribe. Like these videos and share them. Like I've always said in the previous videos, there is actually greatness in humility. There is greatness in humility. The manner in which I cover these videos, the pace at which I move, the level of English that I am using here is not sophisticated at all. And I believe that by so doing, I'm able to carry everyone on board. I do not want accent or the way I pronounce words to be a barrier to someone's learning, right? So God bless you. I'll see you in the next video.